We are now at the point where you guys should be starting to point out that I've been lying to you all year long. And the reason I've been lying to you is to make the math easier, if it makes you feel any better. But we always have assumed that if I have a mass M1 hanging over here and a mass M2 hanging over here, that the tension on this side, Ft1, was equal to the tension on this side, Ft2. And it was only the difference in these forces and the amount of mass on either side that caused acceleration. However, you should be able to recognize that this is not the case. This string attaches here, so if that's Ft2, that's Ft2, and this would also be Ft1. Now if Ft1 equals Ft2, then these two forces are equal. But since they're both pulling equidistant from the center, that means these torques are equal, but they're opposite in direction, and that means the net torque on that pulley equals 0, and that means the angular acceleration of the pulley is 0. The only time that wouldn't be true is if we say, hey, the moment of inertia here is 0, because if it's got no mass, then it doesn't take any torque to accelerate it. But pulleys actually do have mass. So we're going to take a look at how to solve this problem. How do I find the acceleration of this system if there is actually a massive pulley up here? Alright, so I'm going to redraw my picture. I have a pulley, and I'm not going to tell you what its mass is. Well, okay, it can have mass M3, and it can have moment of inertia I. I'll tell you that. Okay? And then I'm going to have a string over here, and over here I'm going to have M2. Not that it matters. Over here I'm going to have M1, and I don't really care which one is bigger, but I'll assume M1 is bigger, and I'm going to give the positive direction as clockwise. Now remember what that means. That means over here up is positive, but over here down is positive. That's just to keep my math simple. Okay, you could have picked the other direction. It does not matter. Okay, I'm going to label everything I know. This is M2 times G. This is M1 times G. This is tension 1. This is tension 2. This is also tension 2. Those are opposite ends of the same string. This is tension 1. So I want to know what's the acceleration of this system. Well, we're going to start with Newton's second law, and we're going to look at this thing, because whatever this thing's acceleration is, the whole system's acceleration is. So on that thing, I have the net force for object 2 is equal to T2 is the positive one, that's tension 2, minus M2G equals M2A. And that is actually what I want to know. So I don't know A. M's I would know, G I know, T I don't know. Okay, so I have one unknown, two unknowns. I need another equation. So I'll come over to M1. So the net force acting on object 1 is, okay, remember positive, so M1G is the positive one, minus T1 equals M1A, Newton's second law for this thing. This A and this A are the same because these are connected by a string. They will accelerate at the same rate. But T1 and T2 are different. So now I have 1, 2, 3 unknowns and only 2 equations, which means I need a third equation. Well, I have a third object, so let's look at that thing. Okay, the problem with this thing is it's not accelerating. It's got angular acceleration. So I don't care about net force, I care about net torque. And the net torque is, let's see, positive is this one, so T1 times R. Remember, the axis of rotation is centered, so this is the radius R. So T1 times R minus T2 times R, this is a counterclockwise rotation, equals I times alpha. Whoa, alright, so alpha is the angular acceleration. Great. Now I have another equation. Okay, R would be known. I could measure the radius of the pulley. That wouldn't be so bad. A is unknown, but that means alpha is unknown. However, I do have one more equation. I do know that the linear acceleration of the system is the angular acceleration of the pulley times the radius r. So I do have 4 equations to go with my 4 unknowns. I don't know A, I don't know T1, I don't know T2, and I don't know alpha, but I'm assuming I would know the moment of inertia of that pulley. So all we have to do is start plugging all these things into each other. I see a T1, a T2, oh, and I'm going to start right here. I'm going to make this replacement. Alpha is really A over R. So I'm going to go ahead and I'm going to do that. So I have the net torque is equal to T1 times R minus T2 times R times, or is equal to, sorry, I times A over R. Now there's actually a relationship between I and R that we might get into here at the end, but for now I'm just going to leave it like that. Okay. T1 and T2 are unknowns, but I have equations for them, or at least I can get equations for them. So I'm going to simplify these real quick. Okay, I'm going to solve this for T2. T2 is equal to M2A plus M2G. And then T1 is equal to M1G minus M2A. Oops, sorry, this is 1, so everything up here is 1. Sorry, M1A. Remember, I basically added this over and subtracted that and rewrote it. So now I can make some substitutions. T1 is M1G minus M1A times R. Okay? And that's this R right here. Minus M2A plus M2G times R equals I times A over R. Okay, now what? Well, let's go ahead and start doing some simplification. Okay, M1G times R, so I'm distributing that R, minus M1A times R minus M2A times R minus M2G times R. So I've basically distributed this negative over here and distributed the R everywhere, equals I times the angular acceleration times, or divided by, R. Now, I really want all my A's together, and I really don't like that R, but we'll see if we can deal with that. Okay, so first I want to do is collect up my like terms, so I'm going to get all my A's on one side. So M1 times G times R minus M2 times G times R is equal to I times A over R, and then I'm going to add over these A's, so plus M1A times R plus M2A times R. Whoa, starting to get complicated, right? Let's go ahead and factor in A out of all these terms. So I have M1G times R minus M2G times R is equal to I over R plus M1R plus M2R all times A. Now, what I want to do is I want to factor this R out. I'm going to. Okay, and there's a G over here on this side. So what I'm going to do is I'm going to factor out the G and the R. G times R times M1 minus M2 is equal to, this is where it gets a little bit interesting. I want to factor an R out of every term, but this one's divided by R, not multiplied by R. So if I factor an R out, what I really have is I over R squared plus M1R, except I'm factoring that R, so plus M1 plus M2 RA. Why did I do that? Well, now this R over here cancels this R over here, and I don't have to deal with that stinking R anymore. So now I have G M1 minus M2 equals I divided by R squared plus M1 plus M2 times A. Sweet. Now if I want A, all I've got to do is divide, so I have A is equal to G times M1 minus M2, that's interesting, divided by I over R squared plus M1 plus M2. This is also fairly interesting. Okay, and here's why. If we go back up and look at this system, T1 and T1 are internal forces. Those two forces cancel each other. T2 and T2 are internal forces. Those two forces cancel each other. We don't care. Basically, the only thing that makes this system accelerate is the fact that M1G is pulling one way and M2G is pulling the other. So this is the force that makes it go, minus this force over here that's opposing that. So F go minus F stop is really what I have down here. GM is the force that's pulling it down, minus GM2, the force that's pulling it the other direction, divided by mass. Now remember, Newton's second law says net force equals mass times acceleration, which means acceleration is net force divided by mass. Okay, and so the top of this equation really is net force. It's the difference of the two forces pulling clockwise versus counterclockwise. And this is mass. And what I mean by that, there's the mass of object 1, there's the mass of object 2, and this is essentially the mass of the pulley. Now, it's not just the mass of the pulley, because remember, if the pulley is a solid disk, then I equals half mass times radius squared. But this is divided by r squared. That goes away, so it could be that. Now, what if the pulley is actually not a solid disk and we had to deal with some other kind of mass distribution? Well, then we would have a different k value here, and so I don't want to eliminate this and turn it into M3 because it's not. It's K times M3, whatever this K value is. However, this does have the proper units, right? Because I is kilogram meters squared and radius is going to be in meters, so it divides out, so we can actually add all these things up. So essentially we have the effective mass of the pulley plus the mass of object 1 plus the mass of object 2. That's the total mass that's accelerating. And then up here we have the net force. So this is just Newton's second law applied with a pulley with mass. Okay. Now, yeah, I agree it's a whole lot easier when we assume the pulley has no mass, because then we can say, all right, well, here's object 2, here's object 1. We have tension, those two are the same, so we don't have to care. Here's F2G, here is F1G. Again, this way is positive. Then I have the net force is equal to F1G minus, F1G, I guess, F2, well, F1 minus F2, I don't care if the G's are there, equals M1 plus M2 times A. Net force equals mass times acceleration. This is a massless pulley. It doesn't matter. It's not over here. But if it does have mass, then we just have to account for that. And it's just I divided by r squared that gives us the effective mass of the pulley. So don't let this problem mess you up. It's not super duper complicated. It's just accounting for the mass that's accelerating when the pulley rotates.